Okay, so today as far as these examples are concerned for divide and conquer, so divide and conquer, we are going to give the last example in this series. Okay, and after today's class, I think the example session will be ended, and as well as one more topic might be remaining that we can cover afterwards, that is master method. Today after this we'll be discussing a little bit about this recursion tree. Okay, so this is about this Strasson's matrix multiplication. So Strasson's matrix multiplication, and first of all will be so matrix multiplication. First of all we'll be discussing that what is the naive algorithm, and then how can we improve by this divide and conquer technique. First of all we will be having a false start, and then by using this Strasson's method we can improve a bit. So this is what is the motivation that we should be studying this algorithm, because this is a very fundamental problem and having many different applications. Okay, whenever we need to multiply two matrices, and in real life scenario the matrices are really big enough. Okay, so whenever we will be multiplying these two matrices, it might be consuming lots of time. So if we can improve a little, that can cause a gigantic improvement. So what we got to do, two matrices to be multiplied, and so this is first of all we are talking about the square matrices for the time being, and maybe extended for non-square matrices as well. So this is say 2 by 2, and this is also 2 by 2 matrix. So this is our X matrix, this is our Y matrix. Okay, and the resultant matrix will be this Z matrix. So the elements of the matrices could be integers, floating points, etc. And here this Zij, so Zij, so that means say this is Z11. So this is any Zij. So here I equals to 1 and j equals to 1. So this is the ith row of X times jth column of Y. So that's how we multiply the two matrices. Okay, so this is 1 2 3 9. So 1 2 3 9 we are having 1 2 3 9, and say another matrix 5 9, maybe this is 2 6, maybe in this example given. Okay, so whenever we are multiplying the two matrices, how we proceed? So one of the ways is this times this. Okay, and we get 1 times 5 plus 2 times 2. So that's how we are getting here. So this Z11, so Z11, that is 1 times 5 plus 2 times 2. So what we can say is that Zij, in a general matrix which is termed as X and Y, so we can say that Zij is equal to, so this is 1 times 5 plus 2 times 2. So this is a first product we are having, okay, and then we are summing it up, right? So we can say that this is summed up over k equals to 1 to n. These many times we have to sum up, okay. So the sum of the product ik times the ykj, right? So this is the idea. So how we are getting this zij, right? So this is for one entry in this resultant matrix Z, okay? One entry. And so here, what is the input size? Input size is order of n square, that is the number of entries in the matrix. N is the dimension of the matrix, so we are having here this n by n matrix, one matrix, and that has to be multiplied by another n by n. So how many entries we are having? So this is this order of n square entries we are having, and this example n equals to 2, how we are multiplying, it is shown here with the symbols, not with the numbers, okay? So this is a b c d, you can put 1 2 5 9 something like that. So this is a AE plus BG, A times C plus B times this G, that we have seen right now, okay? So for this A and this also we can multiply, and that will be getting this. Now this is a quiz, okay? What is the asymptotic running time of the straightforward iterative algorithm for matrix multiplication? So option is theta n log n, theta n square, theta n cube, theta n power 4. So what is your answer? If I am getting this, and the way we multiply matrices, if we are multiplying that, right? So this row versus column, if I am multiplying and then adding, so what will be the asymptotic running time of that straightforward iterative algorithm? For this, yes, theta n cube. Theta n cube we are having, okay? So already what we have seen is that zij, how many this we are having this this is one multiplication, and that the summation, how many times we are having this summation, okay? So n times we are having this summation. So we are having theta n number of additions we are having, right? So this will be taking theta n time. If we expand this, k equals to 1 to n, I am adding up. And how many such entries will be there in this this zij, okay? So this the order of n square entries we will be having, okay? So for order of n square entries we have to do. So that means the overall running time we will be having. So for this zij, calculation will be done in theta n time and order of n square entries. So this theta n square times theta n, that will be theta n cube. So that will be the case for naive iterative algorithm. Now the thing is that we have to chant the mantras that can we do better. So first is yes, Strassen's matrix multiplication, that is using this divide and conquer technique. So here what we are doing is say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 maybe. So this is one 4 by 4 matrices. So 4 by 4 matrices we are having. And here also another say 4 by 4 matrices. 1, 2, 3, 4. Again I can write the same matrix. We have to multiply this. Only I have to show the process. Okay. So this is 13, 14, 15, 16. We are having this. Now what we are, so this is our x, so this is our x, this is our y. So I can write x here, this is x, this is y. So you see this x, we can divide it into this way, that means in blocks of 4. So I can divide it like this. So this will be this is our A, right, which is shown here. This is our A, this is our A, right. So like this way, this will be our B, this will be our B, and this is C, this is D, likewise here E, F, G, H. So this is our E, this is E, and A to H are all n by 2 matrices. Okay. So this is 4 by 4, and this A is having 1, 2, 5, 6. Okay. So this is 2 by 2. That means we can write, so this is 4 by 2 times 4 by 2. That is n by 2 times n by 2 matrices. Okay. In general, so this is here n equals to 4, here n equals to 4. So you should be thinking in general. You think of a 1000 by 1000 matrix. Okay. And then these blocks of A, B, C, D, that will be having n by 2 by n by 2 matrices. So now this, if I am dividing and then if I am multiplying, then this x times y will be A times this E, okay, A times this E plus B times this G, okay. So that will be the case. And this this block will be this A times this F plus B times this H, by following the same principle, rows times the column. Okay. By following the same principle, we will be getting this. So that is proved by, we can prove this by definition of this, that is the multiplication definition, that rows times this column. Okay. So here this first recursive algorithm, what we are getting is, first recursively compute 8 necessary products. 8 necessary products we have to compute. So you see, if I am dividing and then if I am multiplying, right, so then what we are having, AE is 1 multiplication, BG is 1 multiplication, AF, BH, so 4 multiplication, 6, 7, 8, so 1, 2, 3, 4, 5, 6, 7, 8. So 8 number of multiplications we are having. So 8 necessary products recursively we have to solve. And then what we have to do? We have to do necessary additions. So we have to do these necessary additions after this, right? So this way, if I am solving this, then the recursive the recurrence we are having is 8t by 2. That means we are having these matrices, n by n matrices, 2 matrices, and then I am dividing it into blocks of 4, and then I am multiplying this. Then this AE plus BG that we have to form, that we have to recursively solve. So how many such products we have to recursively solve? 8 such products we have to recursively solve. Okay. 8t by 2. So that will be there, 8t by 2. And each of size this n by 2 by n by 2. So this the size is this t by 2, n equals to n by 2 here. And this number of additions after that whenever we are merging. So merging process will be taking theta n square time. So this thing, whenever I am doing this, and then the solution, if I am solving this by using substitution method or master method, then the solution will be coming again Tn equal to theta nq. So as I told you that, okay, if I am using this divide and conquer, then we might be improving. Okay. But this is not the case. Then my claim is failing. If you are arguing like that, then at this juncture I have to admit that yes, the divide and conquer approach that I took, maybe that is a false start. Maybe I will be trying some other method, not the divide and conquer. At this point the Strassens came. Okay. At this point the Strassens came and he showed a clever method, but that cleverness may be based on some kind of trial and error. Whenever I'll be showing that, you can readily understand that why I am calling that Strassens might be having some kind of trial and error and reach this solution. Okay. So next is our Strassens method by using divide and conquer. Okay. So the main idea is we had 8 recursive products to be solved. Can we reduce the number of recursive calls? That is the main idea. That is the question. If I can reduce from 8 to maybe 7, we can improve a lot. And Strassens provide a clever solution for this. Okay. So what he did, he told, okay, we can multiply as we have already seen the Karatsuba multiplication. Okay, Karatsuba multiplication, that is 2 n digits number. 2 n digits number I am multiplying. 2 n digits number. This is 1 n digit. This is 1 n digit, and we are dividing the number. And at that time, the simple recursive solution that gave us t n by 2 plus this, okay, 4t n by 2 plus theta n time, that was the recurrence. But Karatsuba came in and he told that, okay, we can do this by 3 recursive calling, and there lies the improvement. Here also the Strassens is coming and telling, okay, the naive divide and conquer that we are having, that is needing 8 recursive call. but here we will be needing 7 recursive calls. Okay? So that is the improvement Strassens did. Strassens told that you recursively compute only 7 cleverly chosen products. Okay? 7 cleverly chosen products. And that, how did he get that? This 7 cleverly chosen product, that is almost a mystery. And you will see that, okay, he had lots of thinking, trial and error, and then finally he reached the solution. Okay, we'll see this process. And then do the necessary addition and subtraction in theta n square time. That is okay. So he told that my solution will be having, as I am doing 7 recursive calling, so 7 Tn by 2 plus theta n square, the previously what we got. And that solution, if we solve this by using, say, master method or substitution method, the solution will be this: Tn equals to theta in log 7, and this log 7, this is 2.80 less than log 7 less than 2.81. So log 7 is within 2.80 and 2.81. So previously I had Tn equal to theta in cube. We had 3 here. But now n power log 7, that means maybe in between this 2.80 and 2.81, that is less than 3. Okay. So that is the improvement we are having here. But if you are thinking, okay, this is a bare minimum improvement, that is not the case. Okay. So if we implement this, then we can have, perhaps feel the real power of this. Okay. So if I am having, say, 1000 by 1000 matrices to be multiplied, and then we can feel the difference. Okay, so this is the 7 products that this Strassens had. So this is our X matrix, this is our Y matrix, and we are having these blocks. Okay, A, B, C, D. This A, if you can remember, this A is a block. Okay, this is not a single number. Okay, this is another sub matrix. Okay. And Strassens told that, okay, the 7 products that we have to solve is P1 equal to this, P2 equal to A plus B times this H, A plus B times this H. So this is one multiplication here. One multiplication is here, but this is a subtraction. Okay, this is one addition. So then P3 equal to this C plus D times C, P4 equals to this, and P5 or so on. Okay. So here lies the main mystery. Okay. How did he get this this solution? Okay. That means P1, P2, P3, P4, P5, P6, P7. Okay. So here this I am telling that, okay, maybe he had lots of trial and error and he got this. Okay. So this is the 7 recursive multiplication. There are 7 products we are having. We are having to solve recursively. Okay, 7 products. Previously we had 8 products, but now we are having 7 products recursively we have to solve. After that, whenever we are doing x times y, that thing, whenever I am having this, that is equivalent to this 8 product. Instead of this 8 products, what we will be having, whenever we will be trying to get x dot y, then I will be doing simply like this. P4, P5, P4, this P5 already computed, okay. P4 already computed. All these are already computed by that product recursive calling. All these 7 products we have solved, and then we are doing this combining operation, okay. So here we'll be doing this addition and subtraction, right? Addition and subtraction we'll be doing, and that will be equivalent to computing this thing, okay. That means ultimately we'll be getting the right product x dot y, right? So if you are telling, okay, this AE plus BG is equal to P5, P4 minus P2 plus P6, how we are getting, then we can say simply we can put the value and we can compute the result, okay. So this what is this? So what is this P5? A plus D times E plus H. So that we are putting this value. A plus D times E plus H. What is P4? That is D times G minus C. D times G minus C. And this is this way we are putting every value of this P2 and P6, every expression of this, not the value I'll be telling, every expression, sub expression of this P2 and P6 I'll be substituting. And then if I am algebraically, if I am solving this, then ultimately these will be cancelled out, this will be cancelled out, and then AE will be there, this AE will be there, and then this BG is left, you see, AE plus BG. So likewise, if P1 plus P2 if we are adding, then we will be getting this, and then this P3 plus P4 will be getting this, and this if we are doing, then we will be getting this. So after computing 7 recursive product, if I go by this way, then also I will be getting the x dot y. So that is the clever with a question mark, okay. So that is the clever solution of Strassens, okay. So this way Strassens told that, okay, I am doing 7 recursive product like this, and then we are having this theta n square times this addition subtraction whatever, and that is resulting this Tn equals to order of this n log 7. So this is the Strassens idea about dividing the matrices into blocks, and then how we are solving 7 recursive product, and then we are combining like this, okay. So this is Strassens matrix multiplication, okay. So for a few minutes remaining, I can start that one, this recursion tree we can start now, okay. So before going to this recursion tree, one of the things that we have to we have to discuss is that whenever we have solved this say Tn equals to this recurrence whenever we are solving, okay. So we are telling that in the substitution method we have to guess a solution. This Tn equal to order of n log n, and then that means we have to prove that Tn less equal to C times n log n. And then I am assuming that it is true for this floor n by 2, and then we are doing all the algebraic manipulation. Okay, but the method of induction is telling, okay, there are 3 steps. One step is the base case. The base case is true. That base case, and then the assumption, that means it is true for some lower values of n, that is n by 2 floor, and then we have to prove that it is true for some higher values of n, that is n equals to n here. So that is the 3-step procedure, but only we have done this step and this step. We haven't done this base case. So now we can do some kind of some discussion on that. Okay, how to pass this base case, right? So whenever say this, this, so mathematical induction requires us to show that our solution holds for boundary conditions. Okay, so this is from CLRS book. CLRS book, right? So mathematical induction, and the previous Strassen's idea, that was from CLRS, and as well as this Tim Ravgarden's new book called Tim's new book, that is Algorithms Illuminated. Okay, Algorithms Illuminated. From that book I have taken some of the ideas. Okay, Algorithms Illuminated, the first part. There are 4 parts, and if you read this Tim's book, then I think you can pass many difficult interview process. Okay, many difficult interview like Google, Amazon, Facebook, whatever. So this book is not there in the library right now, so you can purchase the Kindle edition from this Amazon, and then you can start reading. Anyway, so typically we do so by showing that the boundary condition are suitable as base cases for the inductive proof. So this that means whenever we are having this recurrence, say this is 2tn by 2 plus n square, say this is a recurrence, and then actually I have to define the recurrence like this. So this is 2tn by 2 plus n square, maybe n greater equals to 1, otherwise 0, otherwise. So this way maybe we can define the particular recurrence equation. Okay, so that means it is showing that, okay, for you can say here, say how you are stopping the recurrence, whether one element in the list and you will be stopping, or 2 elements in the list and then you will be stopping. So based on that, this condition might be varying. Okay, or you can write, say this Tn equals to this, and instead of 0 I can write it is T of 1 constant. So not T of 1, we can write order of 1. Okay, so constant, right? So whenever we are guessing the solution Tn less equal to the Cn log n, okay, and I am putting the putting this value, this straight away, this I am putting this, I am seeing that, okay, this whenever this n equals to 1 value I am putting, or other value I am putting, exactly whatever is written in this induction, that may be satisfying. In some cases it may not, okay, in some cases it may not, okay. So so here you see that for the recurrence of 4.19, maybe that was not shown here, but that is this yes, this is the 4.19 recurrence. So this is Tn equals to 2t floor n by 2 plus n. So for this, for the sake of argument, that T1 equal to 1 is the sole boundary condition for the recurrence. Okay. T1 equals to 1. Then for n equals to 1, so this, the recurrence here, this they are telling that, okay, let us suppose that I am defining the recurrence like this. So this is 2t n by 2 plus this n 2t n by 2 plus n. And whenever this this is n greater than 1, okay, this is n greater than 1, and otherwise it is 1, t1 equals to 1 when n equals to 1. N equals to 1, then this t1 will be equals to 1, and if n greater than 1, then this recurrence we have to follow. So this is the boundary condition that is there whenever we are forming the recurrence. So that is, they are telling, okay, let us assume that this is the sole boundary condition. So now this then for n equals to 1, then now for n equals to 1, the bound, this Tn less equal to 1 will be yielding what? Okay, so you see, so at that time this this c times n log n, c times n log n, and this t1 is what? Okay, so t1, when n equals to 1, t1 is 1, t1 is 1, and if I am putting the value here, this c times n log n, we are guessing the solution that Tn equal to, the upper bound is t c n log n, and I am trying to check whether the base condition is passing or not. That is the sole idea. So in the left hand side I will be putting the value n equals to 1, and from the recurrence I am getting that Tn equals to 1 if n equals to 1. So this is, and the right hand side is coming c n log n. That means c times 1 times log 1. What is the log 1? So c times 1 times 0. So this is 0. Okay. So this 1 less than 0, less than equal to 0, no, this base case is not passing. Okay. So that is the sole point of discussion here. The recurrence I am writing, that recurrence, whatever boundary condition I am imposing, whenever I am checking the base case, that may not pass. Okay. So in that case, what we got to do? So that is the main idea here. Okay. So the inductive proof, so the base case of our inductive proof, fails to hold. Then how to overcome this obstacle? Okay. For a specific boundary condition, with only a little more effort, we can do this. In the recurrence, this 4.19 that we are having here, this 4.19. For example, we take the advantage of asymptotic notation, requiring us only to prove that Tn less equal to n log n for n greater equals to n0, where n0 is a constant that we get to choose. So this is this n0 that we have seen earlier in the asymptotic analysis is coming as the rescuer here. So it is rescuing us from this obstacle. Okay. So in the asymptotically we have to prove that okay Tn less equal to n log. Then asymptotic proof means okay, even if this Tn equals to 1, Tn n equals to 1, that is 1, even if that is not passing, maybe for some larger values of n equals to 4, that we have seen whenever we have done the asymptotic analysis, it may not be passing for n equals to 1, 2 or 3, but it may immediately be passing for higher values. Okay, so that beyond n0, beyond this n0 value, we have to show that it is passing. Okay, so that that we have to do. Okay, so here this if whether this n equals to 2 is passing or not. So what n equals to 2 is telling, what will be the value of Tn, what will be the value of Tn from this recurrence I am getting. So Tn equal to 2Tn by 2. Okay, so this plus this, I guess 2. So T 2 T n equals to 2 by 2, that is 1 plus 2, that means T1 equals to 1, that I'll be putting the value from here. So 2 times 1, that is 2 plus 2, that is 4. And what is the value C n log n is coming? C times n log n. What is the value? So C times this 2 log 2, that is coming. So this is C times 2. Log 2 base 2, that is 1. So 2C. So there is 4 less equal to C times 2. That means we can choose some, say if I am choosing C equals to 1, this is getting satisfied. This is getting satisfied. So that means for n0 greater equals to 2, our base case will be passing. And as we are dealing with asymptotic notation, so our inductive proof will not be hampered here. Okay, so the base case will be passing in that case. So base case will be taking like this. So that is the sole point of discussion. Okay, so today I think the time is up. We can start new chapters. Maybe we can do recursion tree afterwards in between. And first of all, I have to stop this recording, otherwise it will be crossing 100 MB limit.